every year, every person living on this earth uses 2 metric tons of concrete.
But concrete cracks when too much force is put on it, like during an earthquake.
We want to turn brittle concrete into a ductile material similar to that of metal.
What if researchers could make a concrete that bends like metal, heals itself when cracks form, lets first responders know its state before they arrive through wireless sensors and high-speed internet and software called cyber infrastructure?
The world is very complex. We don't have all the expertise here in our laboratory.
From the laboratory to real-world applications, cyber infrastructure is a way to share data, laboratory techniques and approaches, and enables communications with collaborators around the world. Scientists and engineers work together to find, develop, and apply new and better materials that help to build a safer world.
There are many new possibilities for conducting science and engineering research.
Concrete is used more than any other man-made material to build our infrastructures, roads, bridges, buildings. It's strong, relatively cheap. It can be molded into different shapes and forms, and its ingredients are available in most countries. It's made by mixing 3 key ingredients: water, cement, and aggregates, like sand and gravel.
Portland cement is the main ingredient of concrete. That reacts with water to go from basically a powder material into a bonding glue that basically holds aggregates together.
Dr. Victor Lee, a materials scientist and civil engineering professor at the University of Michigan, has been interested in concrete for many years. His focus is on the formation of cracks, a field of study called fracture mechanics.
I got interested in concrete. I felt that there are ways that we can overcome the brittleness, where we can use fracture mechanics at a very small scale.
At the University of Michigan, Professor Lee and his graduate students began developing a concrete that is less brittle. Graduate student Anhua Yang demonstrates concrete's brittle behavior with an 80-pound weight dropped onto a normal concrete block. And this stress test shows how normal concrete fractures under tensile stress. To make the concrete less brittle, more bendable, or ductile, they engineered a material that contains fibers that hold the concrete together as it bends, called ECC, Engineered Cementitious Composites, or commonly known as bendable concrete.
And I recall one of my former postdocs working in our laboratory. He was totally surprised the first time he tested these fracture specimens that leads to fracture toughness similar to that of aluminum. And he was stunned that it was obtained the very first time he tested the specimen. And that may be related to the fact that and perhaps emphasizing the importance of having a theoretical foundation in the design of materials as opposed to empirical design by trial and error. That's what we want to avoid.
When the same 80-pound weight is dropped on an ECC or bendable concrete block, it bends to absorb the force.
One of the important ingredients in the composition of ECC is a very thin coating on the about 20 nanometer scale, controlling the surface of the fiber. And the purpose is to, in fact, allow the fiber to begin slipping and pulling out of the crack, as opposed to fracturing the fiber when the composite is overloaded.
After years of testing, bendable concrete was ready for the real world. Tokyo, Japan is an ideal location. Japan is located in a seismically active region called the Ring of Fire and is prone to earthquakes almost daily.
Like all big cities, we have tall buildings, roadways, lots of traffic going on to highways and bridges and so on. All these are important parts of the built environment. And all these infrastructures, a lot of them are built with concrete.
When the 1995 Kobe earthquake struck a densely populated area south of Tokyo with a magnitude 6.9 earthquake, concrete structures tumbled. The result was disaster. Bringing bendable concrete to the Japanese construction market is what Dr. Tetsu Kanda, former graduate student at the University of Michigan, set out to do.
Hello, Tetsu. How are you doing?
Fine, thank you.
Good to see
Dr. Kanda studied with Dr. Lee's group in developing the ECC material, and now he's overseeing its use in an actual building in Tokyo.
This is very exciting for me because we in the laboratory created the material through micromechanics, as you are aware of, but this is the implementation. See here, a lot of bundles of fibers. That's how they are packaged. Each filament is about 40 micron.
40 micron.
And that's roughly about less than half the size of our human hair.
Right.
So these are very tiny fibers. But once they go into the mix, you want them to be dispersed, separated into tiny filaments.
It was important in the design of bendable concrete that it could be made in traditional concrete plants with little modification. Its first use is in this high-rise apartment building in a fashionable district of Tokyo.
Now we are in the Roppongi district in Tokyo.
The bulky concrete superframe on one axis has been replaced with a single central beam made of bendable concrete.
So it's in the core of the building.
Right.
And they are connecting on every floor the core wall. So that's inside, right in the middle of the building, going all the way up.
Right.
And it helps to resist the seismic load in one direction of the building.
Exactly.
I thought that ECC is a kind of the miracle material. We are always worried about the safety, especially in Japan, where we have a lot of earthquake risk.
Back in the United States, bendable concrete is also put to the test, first at the Grove Street Bridge in Ypsilanti, Michigan. Because of its ability to expand and contract without large cracks, bendable concrete is being used to take the place of an expansion joint. For his doctoral studies, Mike Lepic researched the use of bendable concrete in transportation infrastructures with Dr. Victor Lee.
And an expansion joint is going to typically kind of absorb the thermal movement of a bridge. When it gets hot or cold, the bridge wants to lengthen or shorten.
Right.
And so what we want to do is try to absorb some of that with a material that can actually bend or stretch.
Now, the other aspects that we are working in collaboration with Professor Lynch, he's an expert in the sensor area, and we are working together to create a new type, a new version of ECC, which also serves as a sensor itself.
In the lab, Jerry Lynch and doctoral student Ken Lowe are experimenting to take bendable concrete another step, and that's to sense and transmit its own structural integrity.
Right, so what we're trying to do is we're trying to use the tools of nanotechnology to develop novel types of thin film sensors. Over here are some of our prototypes where we would like to utilize radio frequency identification,
RFID?
Yes, which is a form of passive wireless sensing to wirelessly collect data even when these sensors are embedded into the materials.
By embedding thin film sensors into the bendable concrete, the concrete itself will send out wireless information about the structural integrity that can be accessed by a computer network in real time.
We can monitor strain, cracking, but in addition to that, one of the main things that we want to do is to monitor corrosion.
In addition to self-sensing, another smart functionality being developed for bendable concrete is a self-healing ability.
And the way it does that is by rehealing the cracks. Basically, we can see that what appears as cracks under the microscope gradually get filled in by calcites.
Okay, so this is a crack that we are looking for the self-healing.
Yeah, that's after a few cycles. You can see part of it already healed, right?
When moisture in the air comes into contact with the bendable concrete, a chemical reaction occurs, creating calcites that fill in the cracks.
The cracks are very small, and where fibers cross these cracks, it actually serves very well as a bridging element.
By altering the composition of bendable concrete, scientists are hoping to take advantage of self-healing properties on a large scale. The next step towards the widespread use of bendable concrete is the development of standardized tests.
Describe a little bit the process of these testing round robins.
Right. Well, right now we have a round robin test going on. We have 6 different groups around the world.
For this, Dr. Victor Lee has collaborated with Dr. Thomas Finholt in the School of Information at the University of Michigan.
The round robin test is a means to develop a standardized test method where everyone can use in terms of determining the important properties of ECC.
These monitors set up at the University of Michigan are attached to a high-speed internet, which combined with a special software is called cyber infrastructure. In this case, cyber infrastructure allows users to send video in real time from different laboratories, conducting strength tests on bendable concrete.
There are 2 kinds of things that you want to communicate to your collaborators. And one is about how to set up the test for the concrete material. And the other is to watch the data that's being generated.
And you can see how these cracks developed during the tension, during stringing. So from here you can see more and more cracks developed.
So this captures it over time.
Yes.
And this is the end result of the test.
Exactly.
But here we can follow from the beginning of the test through the end of the test.
Using the cyber infrastructure tools developed in the School of Information, Dr. Victor Lee and his team are able to work with scientists around the world. Scientists can see not only the test results of each group, but how the tests are carried out.
Right, well that's where all the kind of the multimedia content would be really useful, because video is so evocative in terms of understanding technique and application and that kind of stuff.
Cyber infrastructure may also be used to handle the vast amounts of data that would be collected from sensors embedded in bendable concrete structures.
That really fits very well with the original intentions of developing ECC material for safety of infrastructures. And one of the issues, of course, is to quickly determine whether a structure remains safe after a major like an earthquake event or other types of severe loading events.
Regularly, we're exposed to situations where more building information would be crucial. Having that knowledge ahead of time would be a huge help, because we know we'd be going into a safer environment. We'd have a little bit more control over how much danger our personnel are exposed to, and whether or not there's even the possibility of making any saves for rescues for survivors. Information is our greatest ally.
By speeding the rate at which information is disseminated, cyber infrastructure opens a whole world of possibilities. An increased pace of scientific study and the development of interactive materials like bendable concrete are only the beginning.